An array is one of the most basic ways to store data. It's simply a list of elements, all sitting together, each one reachable by a number called its index. What makes an array special is how it's stored. Every element sits right next to the last one in memory, back to back, with zero gaps in between. Because the layout is so predictable, the computer can jump straight to any element instantly, just by doing a little math on its position. This is O of 1, constant time. Updating an element works exactly the same way. Find the address, overwrite the value. Also O of 1, no matter how big the array is. But if you don't know the index, and you're just looking for a value, the computer has no shortcut. It has to check elements one by one. That's O of n, linear time. Adding a new element at the end is usually quick. If there's a free slot waiting, it just drops in. That's O of 1. But inserting in the middle is a different story. Every single element after that spot has to shift over by 1 to make room. That's O of n. Deleting works the same way in reverse. Remove the element, then shift everything after it back by 1 to close the gap. Also O of n. Most arrays you use day to day can grow. When they run out of room, the computer allocates a brand new, bigger block and copies every single element over. That copy costs O of n, but it only happens occasionally. Spread out across many additions, appending to the array still averages out to O of 1. Space is the easy part. Storing in elements takes O of n memory. Double the elements, double the space. It grows in a straight line. Let's recap. Reading and updating by index are O of 1. Searching, inserting in the middle, and deleting are O of n. Appending at the end is amortized O of 1. And space is always O of n. Arrays are the building block behind almost every other data structure you'll learn. Next time, we'll look at hash maps, and how they pull off O of 1 lookups without needing an index at all.